So, welcome everybody for today's talk about in molecular structure biology. Today I would like to talk a little bit about molecular dynamics, what it is, how it works a bit, and what it may be applied for. And show you also at the end, I think, some examples from our own lab, some very simple examples actually, not very complicated ones. So, what is the purpose of molecular dynamics? So usually when you work in structural biology, and you are interested in making structures of this and that, you will find that structures are very nice. You can make fancy publications, but for example, by X-ray crystallography or by NMR spectroscopy or by cryo-electron microscopy. However, usually you get a nice structure, and the structure is a static picture, a three-dimensional picture that is fixed in space. So this is not necessarily telling you anything about what is going on in reality when this macromolecule is, for example, built in a lipid membrane like here, or is in solution, for example, an enzyme, and has to do some conformational changes, to fulfill its function. Could be, for example, the transport of ions or some bound ligands here, or some conformation change during substrate recognition, or maybe also what is also happening, we cannot follow, we have no experimental techniques so far where we can follow a single molecule, how it just at the moment folding up, from an unfolded state to the folded state. We don't have these kind of methods. So what we like to have is to fill this gap. So there are different ways to fill the gaps. When you think about photography back, you can make a series of pictures and then line them up one after the other one. For example, it would be cool when one would make, for example, a series of X-ray crystallographic structures of a membrane transporter in all the different states, or microstates or substates, it actually adopts during the transport process, or the same with an enzyme. Maybe free, it then has the first contact with the substrate, then it folds over a bit over the substrate, then the catalytic residues get into position, attacks and for example, the cis bond, cleave it, relax it a bit, release one part of the product and then the other one. Would be fine to have experimental structures for this, but unfortunately, this is mostly not possible, mostly not the case at all. So one answer to this, and I think one of the major important answers, is molecular dynamics. So where is molecular dynamics actually located? When we look first on the time range. So when we have the time range, we start here from our static experimental structures. They are nice. We can also use some other techniques to get some dynamic information. NMR spectroscopy can, for example, resolve in this time range, in the microsecond to millisecond time range, some simple conformational changes. For example, the flipping of an aromatic residue within the hydrophobic core region of a protein, or maybe the flipping of a nucleobase from a nucleic acid, from a double-stranded nucleic acid. Maybe it can trigger it, you can trigger it, you can then follow a bit, this kind of movement. Nice. But there are other techniques like fluorescence resonance excitation transfer, FRET techniques, which are used in microscopy. They can give you some time range information. You can use AFM, optical tweezers, electrophysiology, actually quite a few other methods. And in the recent times, and I guess maybe that's one or the other topic about in the talks, we have fancy stuff like dynamic crystallography. That means at X fields, or now starting also at conventional synchrotrons, where we can do also dynamic studies as well, providing actually the dream that we had at the beginning. Make a lot of pictures, experimental pictures, and connect these experimental pictures after the other one and make it the movie to get them actually dynamics to see what's happening upon some certain kind of trigger. But molecular dynamic simulations, at least when I talk now about all atom molecular dynamic simulations, that means where we simulate the position of every single atom of a macromolecule, that can be done in the computer. It depends on computer speed and capacities, and it depends, of course, on a few other things actually as well, on the kind of assumptions that we have to do. So molecular dynamics is a very interesting way, to use computer force to provide dynamic information about our given system. For example, as we have seen it before, to see how an ion migrates through the ion channel, to see how a ligand binds. Actually, it's easier to see how the ligand unbinds because then you have a uniform start state, but you can also do the other way around to see how a very small protein nowadays folds, can be tracked up, or some conformation change is happening. But this is done completely in the computer, in silico. So there are the other techniques to get some information. Monte Carlo methods, for example. Monte Carlo means, Monte Carlo, you remember, is where actually you are betting on random numbers. You can make, of course, random moves, also in complex molecules, and to see what's getting out. And by this, you can actually access a huge ensemble. Then when you have just a series of ensembles which are connected again by the timeline of interconversions. Monte Carlo is good, but of course there's no time-dependent information, and that's the reason why we are interested in molecular dynamics mostly, because we get also time-dependent behavior, and we also get something about non-equilibrium processes, which can be very useful. So unfortunately, I have this click down stuff here. So there is also the other issue, the size range. The size range is an issue. So when you go, for example, to theoretical chemists, many theoretical chemists are actually very keen, of simulating systems by using very sophisticated quantum mechanics calculations, using, for example, program packages like Gaussian or GAMES or Orca, where you can actually get a lot of information about the quantum states, also about the absolute energies, about spectra. You can simulate spectra by quantum calculations, or predict spectra by quantum calculation. You can make calculations on electron transfer, get the electron transfer rates out of that, for example, when you are here on a solid phase. But unfortunately, quantum mechanics is pretty weak when you come up to macromolecules, because it only goes to about maybe 100, maybe 200 or 300 atoms, but then it's done. Most quantum mechanical calculations are done with less than 100 atoms at all. So, not suitable for our system. So we have to do a certain kind of simplification, and this simplification is given in molecular dynamics, because now we move from the quantum world, from quantum mechanics, to classical mechanics, to the good old classical mechanics of the 19th century. So in when we do this kind of step, the mathematics becomes much simpler for describing the interactions, because now we are in classical mechanics, and we can now simulate large systems. 100,000 to 1 million atoms is quite typical for an MD simulation in terms of the size of the system that we are studying. We are studying these systems usually also not in vacuum, which you usually also do in quantum mechanics, at least when you do not do some certain kind of semi-empirical corrections, but we do this kind of simulations in water or on given surface. Even we can do simulations in lipid membranes, and to see how a membrane protein reacts. So by just defining a box of a suitable size, where we put our system in, that is somehow hidden here behind a lot of water molecules which are filling up this box. So that's also the reason why we come up quickly with huge numbers of atoms, because we simulate not only the macromolecule that we may be interested in, but we also simulate all the waters around it. Actually, 2 times, 3 times as much atoms are given by the water or by the ions, but mostly water, than by the macromolecule itself. And you know why? Because we have this huge influence of water on all the kind of reactions. There is, of course, also a limit when we are interested in atomistic molecular dynamic simulations. There's a size limit, Clearly, you can do it up to a few million atoms. And I think that is pretty flexible. I have seen now huge simulations with a few hundred of proteins recently. Was very impressive. But there's clearly some limit, Of course, by the computational power that we do have, or we can have at supercomputer places. But there's also some reason to skip that and then go to another technique called coarse-grained molecular dynamics, where we don't simulate every single atom anymore, but then we start, to combine several atoms, to groups which are then linked, by some semi-empirical force or by some guest forces, which are emulating the atomistic systems the best possible way. With coarse grain, we can go longer. So with atomistic molecular dynamics, we have a time range where we can look at usually everything between 10 nanoseconds and 10 microseconds is doable. In our lab, mostly between 100 nanoseconds and 1 microsecond. So these kind of simulations can then go to coarse grain. Maybe pretty helpful. For example, when you ask yourself, can you simulate complete cells? For example, a complete bacterium. The answer is yes, we can do so, but not with an atomistic model, but with certain kind of coarse grain methods, where we simulate a single protein would be, for example, one entity in it that would be given instead of a water molecule. Yes, so it's just a kind of scaling. So there's techniques for going to continuum models and these kind of things, but far off from the size range of atomistic stuff. Unfortunately, this is clicked down here again. I made a mistake when preparing everything because it was done very quickly. So I guess many of you have not listened very carefully to thermodynamics, which is a bit pity because it can be quite useful to have at least the basics always in mind. Hopefully you have some of them in mind. I keep it simple. Just tell you something. So these boxes are now filled. So this will be our statistical ensemble because we make a simulation through time, and every single given time point, yes, that we do have is contributing to the whole system behavior. So that is a quite interesting, it would be quite nice, when we could do it in a way where we could look on a million molecules at the same time, how they react, a million lysozyme molecules, simulating them, yes, and see how they do react. That would be pretty cool when we could do that, but we cannot do so because of computational limitation. So that means that actually our ensemble, our collection of states, is given by the different time points that we do have. Here are some other points about this canonical partition function Q. Yes, defined as a dimensionless number describing the statistical properties of a system in a thermodynamic equilibrium. So what we would like to get with our molecular dynamic simulation is to be in a time range or to have the system equilibrated enough that it's behaving like it would be in a thermodynamic equilibrium. So that everything that we can learn from how it twiggles around and deals around with and has some kind of dynamics is representative of the system in the thermodynamic equilibrium. Just to remind you a bit, just imagine you are not in the thermodynamic equilibrium. Atom 1, atom 2, they are linked by a covalent bond, but they are 6 angstrom away from each other because maybe you made some mistake with setting up your system, or maybe because you set up your system and you have some little errors in it. Yes, clearly that goes together, very quickly. It's non-equilibrium. It has to go to some equilibrium distance, so that everything that you can learn from this, and also the influence on the surroundings are representative of the system. So that's a classical canonical partition function Q, you know the Boltzmann factor, that is the energy of the system I here, for example, some state, yes, that you do have, clearly, one of the reasons, to get as many different states at hand as possible to get large ensembles. There are different kind of ensembles that we can get. First ensemble is just this one, the classical partition function with this here, with this energy. E is energy, and beta is some factor, minus kt logarithm q, and the A is a Helmholtz energy, the classical Helmholtz energy, U minus Ts from a closed system. So you have a box and it is simply closed. Nothing is changing. Volume is constant. Number of particles in it is constant because nothing can escape from it. Temperature also constant, So that would be the classical closed system that we have, in this way. There are some other systems, For us of largest interest is actually this system, the NVT system and the NPT system. So the NPT system is assuming that actually we have a system, a box, for example, that is in equilibrium, that is constant in terms of its particles inside of it. The particles are constant, they cannot go out and in, they cannot escape our box. The temperature is kept constant by coupling it to a heat reservoir and by computational means. So you could imagine you would have a reservoir around it, but actually the computer simulates it, yes. And actually that the pressure is constant. For example, 1 bar, 1 atmosphere. The pressure is constant, which is not the case with the system where the volume is constant. There the pressure is fluctuating around. Here we assume that the pressure is constant because, and you can imagine, this is the most relevant system that we do have, pressure is constant. So that could mean, for example, that the box size fluctuates a little bit in equilibrium because always a little bit fluctuations, yes, of these systems, also in terms of the box size, yes, of the size when you have a given number of atoms which you are putting in. Oh, come on. I have a lecture, sorry. So that was the telephone for the next hour, or 3/4 of an hour. Okay, so that's about what is this statistical ensemble. So we'd like to try to assemble the ensemble as best as possible. As best as possible means mostly as long as possible. Okay, unfortunately I have to click it down again. Sorry for this mistake. So we said it's classical mechanics. How is it now working? Molecular dynamics. Actually, it's very simple. You have an atom at position R. R is the vector that points to that gives you the position of the atom. The issue is how to get the position of the atom when going from the time t to the time t plus delta t. You know that how it goes. Yeah, you should know it at least, yes, Plus delta t times the velocity of this atom at this position R, yes, times the velocity, that's also the direction, yes, where it goes to, plus, and actually because that is now an approximation here, you see that the series up to the second term, yes, so the second derivation of a position against time, the first one was velocity, the second one is acceleration, is delta t to square divided by 2 times a the acceleration, of the atom at the position t. So that's the point, yes, the very basics. And the acceleration you can also calculate by taking the force, the force that my atom gets at a particular position, t plus delta t, divided by its mass. The mass of atoms, is tabulated. So you can put this in, and also the velocity, you can also calculate it at the time t plus delta t. It's the velocity at the time t plus blah, 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 let's say the average value of the acceleration, at time t and time t plus delta t divided by 2 and multiplied by delta t. So that is actually the most basic equilibration equation that we do have for molecular dynamics. Of course, you have to assume, the R, is for one atom, but it may stand for, you may have a million of these equations, a million of those, and for every time step, they have to be evaluated. Very time consuming. And actually, these kind of equations are also pretty broad approximations. So just to remember here, so how we go on, we have first, we calculate the forces at the time t plus delta, actually, I should correct this. We calculate the new particle positions using classical mechanics at the time t plus delta t, that is this one. We calculate all the other rest as well, using the correct delta t. The delta t is very interesting because it is called the step size. Come about this. Then maybe number 3, we apply some damping factors, corrections, coupling to thermal reservoir, etc., to get the system, well behaving and stable. And then set now t to t plus delta and go back to 1 and do this. And do this millions of times. Sometimes maybe billions of times, spending computer weeks and months. So this calculation intense process, provides then trajectories at all these given time points which are separated by the step size. So when you make a simulation, 100 nanoseconds, 2 femtoseconds, 2 femtosecond step size, you have about 500, 500,000, 50 million states. Okay, you cannot write them out all to the computer because your hard disk would crash down. Maybe you write out just not so many, but just a few thousand of them here, separated by a few picoseconds. Very computer intense. Unfortunately, I have again this kind of click down bullshit. So this is also what is the optimal step size. So the optimal step size should be, of course, as long as possible that the simulation is stable, but short enough to prevent that the simulation is crashing. So the step size is usually less than 2 femtoseconds. And the reason for that is fairly simple, because we have to take care what is the fastest motion in any kind of classical simulation when we have a certain kind of bonds between atoms. So CH stretches, for example, they should have, I think, a lower frequency than the OH stretches. Yes, stretching motion. Yes, this one. When you take the step size too long, yes, like this one, for example, here, yes, you put the system far off here from its energy potential surface. Something happens, the system is in a non-defined state, it crashes immediately, yes. Step size is too long. When the step size is adequate, you move here around, you mostly stay here, on your energy potential phase. Simulation will keep stable. Or just imagine, you have a too long step size. Maybe the hydrogen atom, in this bond is suddenly too far away because it was overestimating the velocity it had, in this direction, yes, and you multiplied it by the time delay, and it's not 1 angstrom array, it's 3 angstrom array, yes, and maybe everything breaks down. So, there is some problem with step size. So that we can actually get up to 2 femtoseconds, we can only say that it's because there are some algorithms working in modern packages, that actually take care of this, of the very fast vibrations, of heavy atom hydrogen bonds, like the shake algorithm. So otherwise, we would have to use much shorter step size of maybe 0.5 femtoseconds or less, which is not good because that takes in more time, yes, for a given kind of time. And here I have a lot of fancy equations copied from the internet, very fancy, but just to show that to you again, yes, So there are, of course, the different ways how to calculate positions, So we have seen one before, that was this one here, the very basic one. This one, yes, the very basic one, but there are better ones, and they're implemented in modern programs. That was a super basic one, the leapfrog algorithm, very old actually, yes, very old, even simpler than the one we have seen before, you know. Um, Maybe sometimes useful when starting something, but or to shake something up. But leapfrog is mostly not used. I mostly use more complicated ones. For example, you see here the Vallée algorithm that is similar like the one that we have seen before, but it has a third and a fourth term. Third and a fourth term. And the advantage is why to use these more complicated equations, yes, where we have additional terms, is that the delta t can be made longer. The step size can be made longer when using more sophisticated algorithms. Actually, nothing we have to take care, but the programs will provide it. So that's something about that. So I talked about forces on atoms. So these forces have to be somehow evaluated and calculated. There are different force fields, for example, Charm 27 or Ember force fields like FF14SB, They are all, the general idea is always the same. They use classical assumptions, and they use very simple model, very simple model, for example, for the bond lengths. Yes, this one here is, for example, simulated by a parabola. It's just Hooke's law, that we do have, just enough, for making on that kind of range, that kind of simulations. Clearly, it's not quantum chemistry that we are doing here. You can use also Hooke's law on angles, yes, and of course, related one, using the periodicity of our rotations around torsions, yes, torsion angles by this cosine stuff there. Pretty simple. That is for everything that is bonded with each other. This one, it's the internal energies that do come up. These actually have been the energies here. So what about the external energies? Now, the external energies are mostly two types: van der Waals interaction, Coulomb interaction. These are the two major ones. And there are also some simplifications going on. For example, that one is not calculating them out, not for, for the interaction between atom 1 and 2, for example. It wouldn't make sense because they are already covalently bonded, yes, So it doesn't make sense to evaluate a Coulomb van der Waals potential here as well. Actually, that is being usually lumped up here in the other parameters here in the internal description. Also, not 1-3 interactions, also mostly not. We have this described for the angles, yes, it's already coded in. But maybe 1-4 interactions, that between this atom and that atom, that have to be considered. So, okay, so going to some of the very basic ones. Let's go first, to the external ones, yes. So of course, this Hart-Seum model. Hopefully, everybody can remind you physical chemistry. I like this topic so much. Here with this kind of gas equation for Hart. I love this, but you not, maybe, or some of you not. The Lennard-Jones potential is the most accurate one that we do have. It's described here. Yes, with its parameters. Usually pretty good. And actually, that is also the one that is usually used. The Lennard-Jones potential, or suitable approximations of the Lennard-Jones potential. Here LJ for Lennard-Jones, like in the charm force field. Just two parameters are necessary to describe the interaction between atom type I and atom type J, for example, between carbon atom, or oxygen atom, hydrogen atom, mostly just these two parameters are usually enough, but you also have to know, of course, the atomic radii. And there, actually, you see, you actually you see a lot of correction factors here coming in, yes, which are made by these force fields, because the force fields are very often derived, from quantum chemical calculations to make the best classical guess how the system would behave. One sees whether the system is well behaving by making long runs of these kind of systems and comparing that with what the quantum chemistry has calculated and what the experimentalists have actually measured, to get this force field consistent with theory and experiment. But these individual parameters, they are just, yeah, treated, just optimized, yes, by mostly to give the most suitable result of the system. That is for the Coulomb interactions, also between these two atom types. Coulomb interaction also pretty simple. We need the charge, the partial charge of the given atom, which is very important. Water, for example, minus 0.834 is the charge of the oxygen, and plus 417 for the hydrogen atom, for the proton there. And here for this carbon, it depends which carbon here in arginine, actually. Very good question. I don't know which it is, with minus 0.18, maybe the carbonyl carbon, So you see, carbon is not carbon. In arginine, we have at least 4 different types of carbon atoms, in the amino residue arginine, which belong to different atom types belonging to the same element, to carbon. The carbonyl carbon, then the carbon in the guanidinium group, yes, the C alpha atom that is linked with the amino group and this carbonyl group, yes, with the peptide group. 3, and number 4 would be then the other atoms in the side chain. However, probably it's 5, because the carbon atom next to the nitrogen, yes, of the guanidinium group would probably also give a separate type. So at least 5 different carbon atom types in one amino acid, and everything has to be tabulated how this interacts with all the other ones. Endless data, but actually everything has been done in decades of work, to be available. So for the Coulomb interactions, the charge interactions, they have a pretty long range, where you can see Coulomb interactions, because Coulomb interactions go in with, as you remember, at least me, I remember here, where is the Coulomb interactions? With R2 minus 1 distance to minus 1 for the energy, and R2 minus 2 for the force, so they are pretty long range compared to the van der Waals. And that means these kind of long range interactions, in general, we would have to calculate them, for all the atoms in these boxes, because they go to 10, 15, 20 angstrom without any kind of problem. However, that would give a combinatorial explosion of interactions you would have to calculate. And that means, one has to make cutoffs. And here the typical cutoff shown at 15, 12, and 10 angstrom cutoff. You reduce the number of interactions and of variables by this you have to calculate with, and by this, you can come up to considerably larger simulation times than when skipping this. Clearly, everything has then to be a bit dealt around in the region where you then go from the normal Coulomb potential that you have emulated with your force field to 0 when you're far off here by a region that is switching it, that is getting this from this line to that dotted line down here, so that you don't have to calculate the long range interaction. And that makes, of course, some errors in this kind of calculations as well. So maybe something about these force fields, yes, Their usual ones or many ones are the all atom force fields, where every single atom is described, also the hydrogen atoms, in number and charm, standard method, you know. Um, there are also united atoms approaches, which actually combine the hydrogen atoms with the heavy atom in one group here, methylene group or methyl group, you know, and making some empirical force fields, which are simulating the interaction with. It saves a lot of computing time already because, as you see, the number of hydrogen atoms is usually 2 times the number of non-hydrogen atoms. One can go further. One can go to coarse grain, where you are not going to the very elemental groups, but maybe where you say in coarse grain, I take now as a dot now the full side chain of amino acid, and then just make them different kind of side chain types. Yes, 20 different types, as we had seen it before with different atom types. Yes, where we had 5 different atom types all around for arginine. Yes, for carbons. Yes, so you just say, okay, then I have 20 different side chain types and maybe one main chain type. Yes, or maybe just 2 main chain types. Yes, and they are linked with each other by some by some force field that gives behavior that looks more or less normal. For example, also when you like to simulate large lipid membranes. This is as example here, for example, this is the head group here that is dot 2 is the part, you know, of the beginning of the lipid here with the glycerol moiety and the ester bonds, yes, you know, and the third blob here is just, you know, the rest of the alkyl groups of the fatty acids. So the lipid that had before 100 atoms, yes, you know, is now reduced just to 3 blobs, which you cannot ask certain kind of questions with this kind of model, but you could, for example, look how a membrane as a whole may fluctuate a little bit, or what would happen when you heat it up or something like that. And then the other things that you also have to keep in mind is models that you are using for water molecules. So there are also different water molecule types, you know, which are mostly the most highest sophisticated gases of water, being able to react with classical mechanics in a similar way like water usually is doing, where you would have to apply quantum mechanics because water is an unusual liquid anyway. So one of the famous water types are the so-called tip4p water molecules, you know, which are defined by the 3 atom types, you know, by a central point here, where that is here, this endpoint where they are centered here, you know, by some, of course, distance for the oxygen, hydrogen, partial charges, etc., you know. But there are, of course, approaches of simulating water just by a sphere. Yes, you know, by just this sphere here would be fancy, yes, you know, would be simpler. But this is more accurate. With this model, you can predict the actions, yes, you know, between water and side chains and in an active site when you make an active site study. So the water models are very important for all the simulations. Yeah, okay. Or you make a hybrid approach and make everything here at high resolution, very atomistic model, and then do this kind of blurbsy SPC waters or something like that around it. Fancy. Can save some time, maybe. Okay, so these are all the kind of interactions you now know, and you know the source is quite often quantum mechanics. So thanks to theoretical chemistry, you know, also to experimentalists from the physical chemistry department, yes, you know, they produce all these kind of fancy numbers, yes, you know. So when, for example, Carl Friedrich Weitzel decides now to measure the vibration spectra of hydrogen chloride now to the 10th digit after the comma, you know, this is not absolutely useless. Quite the contrary, it may be useful for some force field. Okay, for a force field maybe where you would simulate maybe hydrogen chloride in the gas phase, yes. But you know, there is some reason why these kind of data are very, very useful, very accurate data, you know, getting from experiment and from calculations. So these are here some old numbers. You see, it's from Samara Schlick's book, yes, from 2010. You know, about the number of atoms that we had in the systems, yes, and how long we could calculate simulate these systems at that time, yes, you know. So how long we would take to calculate a nanosecond. these are old numbers. They are 10 years old. So um, at that time, you see, it looks like that you could come up with maybe just a few nanoseconds per day, yes. But I can tell you, that, for example, this lysozyme simulation with that kind of range of protein, we would probably go for about 200 nanoseconds per day, yes, in the lab would be no problem. And what is the reason that we can do so nowadays? That we have much faster access, because it's of course calculated per CPU, per core in a central processing unit. So your computers probably have 2 or 4 cores that you can do some your computer work on it, When it tells you, naja, you will come very far with this. Yes, you will certainly not do on your computer molecular dynamics simulations. So the progress, that has been done is progress in hardware. So the first progress was progress in the force fields to get stable force fields to simulate meaningful stuff. But the second issue is hardware. So in the past, all larger countries and also larger universities had large computing. They have large computer centers also still nowadays, and mostly with a few hundreds and thousands of CPUs, yes, in this kind of setups in. So this is still the case, but everything is expanding now. So it has been found that for molecular dynamic simulations, we need quite a lot of cores, but these kind of cores can be provided by graphics cards nowadays. Maybe some of the hardware affine people follow a little bit, or who like computer gaming, yes, follow a little bit up the development of graphics cards. So graphics cards are nothing different than highly parallelized computing units, where actually a graphics card is made, every computing unit is made for calculating the pixels for your screen, yes. So when you play some damned computer or online shooting game in high resolution, the graphics card is calculating all over the time the shading and the light and the resulting pixel color, of a given system. That is pretty close to what we are doing. So we use graphics processing units, graphics cards, to do molecular dynamics calculations. And the number, of CPU cores, a modern 2080 card, this is a slide for the 1080 card, the modern 2080 card from NVIDIA is making is in the range of about, I think, 300 CPU cores, yes. So you can assume that when you do a calculation on the graphics card, that it goes about 200 to 300 times faster than on your CPU. So that's a point which is also cost effective, because GPU, it costs a lot of electricity. Some people who like gaming knows it, but compared to 300 CPUs, it consumes much less power, yes, because maybe it consumes 200 watt, yes, and it means a single core consumes less than a single watt, yes. So that's something you can do, and modern programs for molecular dynamics like AMBER are actually optimized for running on this kind of GPU cards. So that is actually the reason, why we have now access to molecular dynamics also in a time range that is interesting for us. When I have been a student like you in the 80s, papers have been made in Nature and Science where people simulated for 100 picoseconds some enzyme, and we're making some conclusions about the catalytic mechanism. Just imagine, today you would probably to say, naja, something comparable would be to do maybe 100 microseconds, yes, so 6 orders of magnitude longer time, yes, you can ask completely different questions about it. So this is an overview about this kind of force field which are accessible, and the graphics program and the programs. The most famous ones is ENBA, GROMEX, which has been also developed in the 90s for use on PCs and now also running on graphics cards as well. And AMD is not so much anymore in further development, I think. So Gromex and Amber, and also the Charm package, which is also now running now with completely on the graphics unit. So it should be also a bit marked here because it's also a very interesting system. So that is all the kind of programs which are available. So what about the simulation now? We have now talked about a little bit about these issues. Not finished yet. So just imagine, I said we put everything into a box. Point number one, what is outside the box? So outside the box, in general you could say, naja, there could be vacuum. But when there would be vacuum, your water would evaporate through the boundary, yes, or would be just being, let's say, bounced back by the boundary here, when you would say, I make here a hard boundary. That is not very realistical, yes, Clearly, when the water starts to go there, or the macromolecule starts to move there, it also moves, it goes on, yes, it does not stop, it will not get reflected here. That gives nonsense results. So a simulation in vacuum for the kind of system doesn't make sense. Clearly you could put it into sphere to simulate a little droplet in the mass spectrometer. Yes, that is just evaporating. You can do so. Maybe also would be also some scientific issue to do so. Actually, indeed, yes. But for this kind of conventional simulations, where we just ask some questions about molecular dynamics, the dynamics in the molecule, whether domains are breaching, lids are flapping, yes, whatsoever. This doesn't make sense. So the solution is to use periodic boundary conditions. So you have the box, and in every other box, they are not calculated. They are exactly identical to this box. They are identical because you invent a rule indicating that, for example, when this molecule, for example, the water molecule, moves here now across the border, like here, it enters at the opposite side of the box in the system again. So this is a slight distortion, this is a slight lack of reality, but it's something that can be tolerated. By this, it's somehow like you would simulate a crystal, which is not absolutely true, because in a crystal, every box in the crystal would be a bit different from the other ones, and you would see by crystallography the average of those ones. Yes, in this case, they are all the same here. So with this kind of ensemble, using periodic boundary conditions, we can define the used ensembles, the canonical ensemble, the NVT ensemble that we have seen before, and the Heisenberg thermal ensemble, the NPT ensemble, constant pressure, constant temperature. These are the two most used ones. What about the size of the box? Usually 10 angstrom, 10 to 12 angstrom from the surface of the macromolecule. So usually you try to solvate everything with water, you fill it up. What you also have to do, also keep in mind, it should be electrically neutral. So there should be no positive or negative charge remaining inside this box. So you would have to neutralize your charged protein with counter ions. For example, the protein has an overall charge of -10. You would have to do at least to add 10 sodium ions, into the box as well to counter the charge. And usually you add more to simulate a salt content, for example, of having a salt content of 0.1 molar. That is a bit more realistic to have it. Okay, so that would be about how to define that kind of systems. There have been also made some proposals, of using different geometries. I think the Gromex people made this pretty fancy. There is actually some reason to do so. For example, you would like to simulate something that is, for example, elongated, like double-stranded DNA, and you would put this into a rectangular box. You would have a lot of corners, where you would have to simulate additional water molecules in the corners, which you do not need really, By making this in a hexagonal cylinder, you can make this system smaller. You can simulate longer times, yes. It would be also a bit more isotropical here around the duplex DNA. So you could do so, but, it's only interesting for certain specialized systems. some specialized systems, yeah, for example, membrane systems, that may be some reason. So then we have said, there are also different kind of flavors for in silico simulation. So what I talked before was molecular dynamics simulation. Molecular dynamics, that is given at a given temperature, 300 Kelvin mostly. When you would do the same at T equals 0 Kelvin, that is actually called minimization, where you actually try to minimize the energy and of the system. Because at T equals 0, there's no motion, no thermal motion anymore left, no thermal diffusion anymore left, nothing like that. So minimization is usually done at the very beginning of any kind of molecular dynamics study, because when you have a given system, for example, you built it, you construct it from some given structure, filled everything up with water and this and that, but there are still a lot of conflicts in it. The first thing yet you have to do is to get rid of energetic conflicts, van der Waals conflicts, etc., so on. So you minimize the system by energy minimization of the system at T equals 0. I don't know, but you should know there are different kind of methods to do so and to minimize a system. These are numerical methods, very powerful systems to minimize this, the structure of a system. Clearly, the minimized structure is not the real structure necessarily. It's just a structure that is free, from clashes and that kind of things. And to see whether the parameterization, everything is fine and okay. So that it goes fast. It just takes a few minutes on the computer. So the molecular dynamics, we have talked quite a bit. Yes, for example, here, learning something about DNA motion in DNA polymerase lambda. Yes, you can simulate how it moves through. Very fancy, yes, can learn something about the importance of certain residues in this process, make maybe some mutation, check it out, whether it's really so useful. Then Brownian dynamics, it's something more on the coarse grain simulation. Yes, here you simplify your system considerably. Yes, for example, here supercoiled DNA is more or less like a rope now. Yes, with some segments in between. Start to simulate to see how it's knotting up. You can simulate, of course, tens of milliseconds, maybe even seconds with this. In time, but using, of course, the computing power. Monte Carlo I talked about at the beginning, but this is a method you do not get any kind of time-dependent conformational change or transition, but you can map out a bit the energy scape, yes, for example, of a given system and the kind of conformation that are consistent with that. And the other interesting method is targeted molecular dynamics. So, for example, you ask yourself, what is important for the binding of a ligand to a receptor? How would you simulate this? The naive way would be to put the receptor in the box, to put the ligand in the box, and then let it run for weeks whatsoever. And maybe sometimes the ligand hits the receptor at the correct, at the right side and also in the right orientation, and then it starts to dock and to form the proper receptor ligand complex. But you have to wait quite a long time maybe when you are in bed. But you can also do it in the other way around. You take the receptor ligand complex, yeah, which is defined, maybe because you have a structure, and then you start to apply a weak force to pull out a little bit, on the ligand, and you can apply this in silico during the simulation, yes, and see how the protein reacts. So when you do this sufficiently slow, that the system is almost close to equilibrium at every given time, you can see the dissociation pathway when the ligand gets off from the receptor. And when you have a bit of luck, the dissociation pathway and the association pathway are the same. So in that case, you can use targeted molecular dynamics for getting some information about a process that would usually take ages to follow that up with this kind of methods. So this is also a summary of all these kind of different methods, Also here, a general way how you do this kind of molecular dynamic simulation. So in the first beginning, here you do first, before you start anything, you do energy minimization. That is missing here. So you have the system filled up in the box whatsoever, you do energy minimization. That goes very quickly. Then when this is minimized, then you start. The first thing is you start it up with heating. Yes, you go from 0 Kelvin, that corresponds to the energy minimization, to the temperature at energy minimization. That's the same like molecular dynamics at T equals 0 Kelvin. You heat it up to your temperature, to let's say 300 Kelvin over some given time point, the time range. Here in this example, 10 picoseconds. Then you let the temperature constant, yes, and then you let it run, and let it run, and let it run, and let it run, and let it run. And then after some time, you say you look on some of the characteristics of the system, and then you can decide, okay, it looks like that my system, some global system variables do not change so much anymore, So what is coming now is a time period where I can go now for production, where I can now make trajectories, which go for long time ranges, nanoseconds, microseconds, whatsoever. And then, when you have calculated these kind of trajectories, these long-term trajectories, then you can also do some evaluation, what's going on, which residue is how often in contact with the ligand, or is it having alternative interaction partner, and do all this kind of evaluation, for this kind of system. Because the production run, the production time, the time during the time interval for your production run should be a time interval where you are sure that your system is in thermodynamic equilibrium now. It's equilibrized. So that about the general strategy. So let's look here for some examples. Hopefully it works. Some example is, I think, from some of our collaborational work with the genetics department here. It's biology. It's dealing about adhesin molecules which are on the surface of pathogenic yeast, fungi, Candida glabrata in that case. Candida glabrata is a yeast-like organism, it's a eukaryotic organism that lives in our gut, on the surface of our skin, and can cause also some troubles, as you can see here on the next slide, So here, when you have this kind of tongue, yes, it looks like Candida, yes, it looks nasty, yes, not very nice. Vaginal infections are also very often, but male colleagues should be careful, We do not get affected so much by this, because it's a different topology that we do have. Candida is okay usually, yes, but when it's an opportunistic pathogen. So when you are immunocompromised, yes, so you are a bit elder, maybe you're in the 80s, yes, the fungi can kill you, yes, when you have bad luck, yes, or when you have to take some immune suppressive medication, yes, or you are under intense care medical treatment, like here in a hospital, where maybe somebody put you a catheter in it to get the urine out of you. Unfortunately, this these catheters with the PET material, very good. The Candida do adhere very well to this plastic surface, as you see here. And this is actually mediated by these adhesins, yes, just mentioned before. So there's a problem, yes, with fungal infections. Actually, that is also the promise for the future, because everybody's in Corona mode, yes, you will see fungi will come. It's only a question of time, yes, Fungi are very dangerous candidates, yes. Very difficult to treat, actually, because they're eukaryotes like us, yes, and they're pretty well-wised, to survive a lot of antifungal compounds nowadays. It's a problem. So this adhesin actually binds to this carbohydrate epitope, yes, it's two sugars, galactose and glucose. And the funny thing, at that time when we made the structure, and it was published in PNAS, was we crystallized the protein in lactose. So when you have learned a little bit your organic chemistry quite well, or your biochemistry, you should know that lactose is galactose beta 1,4 linked with glucose. but in the structure it's beta-1,3 linked. How can this be? We crystallized this protein very nicely in the presence of 0.5 molar lactose, but we get this, very fancy observation, that we made at that time. And to come to this point, also a bit more in detail, there are many more adhesins in Candida glabrata, actually fungal organisms. Some fungal organisms, especially the pathogenic ones, have almost batteries of adhesins in their genomes encoded, different ones, but they are all related with each other. So, for example, the Candida glabrata codes for 20 different paralogs, clinical isolates, can code for up to 20 different paralogs of this EPA1 adhesin. They are all related with each other. They all have the same overall structure. They are similar. Clearly, we did structure analysis of those ones and analyzed the specificity profile and found that the specificity profile is different. Some of them can accept gal beta-1,4, some of them prefer gal beta-1,3, actually like EPA1, Some of them are a bit more relaxed about this. So, for example, here was a question at the very beginning, when we came up with this kind of story. Hopefully, I have some movies somehow working here in this presentation. Was a question: why did we get the crystals with the contaminant? Because when looking on the bottle of lactose, 98% PA. Clearly, we always buy the best chemicals for our kind of experiments. I was then asking, what are the other 2%? Because at 0.5 molar concentration, 2% contamination means that is in the millimolar range, yes. And actually, you do find that there are contaminants, lactosamines, and that kind of things present, which also comprise this kind of substructure, gal beta-1,3 gluc. So actually, we crystallized something that was a contaminant, but not with the major component, the beta-1,4 link. So the question is, why did this one crystallize and this one did not crystallize? Stupid question, but very interesting one. It was a 20 nanosecond simulation at that time, and let's see whether this kind of movies go on. So in the beta-1,4, we see here that actually this aromatic residue that is packing or should pack is pretty flexible, and also that the sugar is pretty flexible. However, in the beta-1,3, with the beta-1,3 sugar, the complex stays stable. This is very well packed. And that has an effect because when you look on the movie here on the left-hand side, again, you see, because this one is more mobile, everything else is also more mobile. Also this loop region here below it, whereas in the other case, everything is here tightly packed. So that was the reason why it crystallized and not the other, not the other complex. Also in solution, the other complex was probably had a higher concentration than the wrong one. Okay, now we have seen it enough, yes? So what else is to be mentioned, in this case, so what we also did find, during the study was that actually there is a tryptophan residue that is conserved only in this kind of EPA adhesins, but not in other adhesins which are very related, which also do bind some carbohydrates. It's a tryptophan, and it's actually packing pretty next to the galactose. And also, when you find for conservation in other Candida-related species, you find tryptophan, sometimes the tyrosine residue. The question was, what is its role? Clearly, from the structure, you would say it packs somehow, but is it important? So clearly, you can also do some validation. Let's see where it goes. Now, I want to go one slide. Oh, it's taking a bit of time. Computer is slow now, suddenly. What is? So I think with this not happening movie at all, which looks like a characteristic computer crash, yes, at least a crash, of PowerPoint at this position of the talk. But actually it was also the last slide, yes, so we are not missing too much about it. I would say many thanks for your attention, and I guess I'm open for questions as always. Thanks a lot. So.